Welcome to part 10 of Zombies and Reinforcement Learning. In part 10, we're finally going to move from the zombies portion of this to the reinforcement learning portion of this. And the first thing we're going to do is build out our buffer.py, our buffer class. So just as a reminder, when you're dealing, and we're going to be using a double DQN. So, standard Q-learning. Q-learning is going to take an observation from an environment, and it's going to directly predict the results of, it's going to directly predict the value of a given action in a given state, and then it's going to use that prediction to go in and take an action on the environment. So let's talk about how the buffer plays in for a moment. So in Q-learning, we're going to have our agent, and we're going to have our environment. And I'm also assuming, again, the whole focus of this has been building custom environments for OpenAI Gym. I'm kind of assuming that you're not a complete beginner to Q-learning. This is not intended to be a full, how to do DQN course. There's much better content out there for that. I'm not going to try to recreate it. But we'll just do kind of a quick map out of what we're doing. So we have our agent is going to be taking actions on the environment. The environment is then going to return an observation to the agent. So agent takes action, environment produces, and hopefully you can see that well enough here. Let's blow it up a little bit. All right, so agent takes an action on the environment. Environment returns an observation to the agent. The agent is going to take that and store it in a replay buffer. So this is the actual, action happening. This is no learning is happening in this. This is agent, environment, observation, back to agent. The agent is then storing that in a replay buffer. The training process, so we'll just call that, we'll say this is the learn method. Learning. The learning process is going to take a batch from the replay buffer. So we're basically taking a, a lot of what we end up doing in reinforcement learning is taking an unsupervised problem like, RL in an environment and treating it like, a supervised learning problem. So the learning process is going to pull a batch of observations with rewards, info, etc. from the replay buffer, and it's going to, go and process that, check the value. We're going to get a loss. It's going to use gradient descent to try to improve that loss value, and then ultimately it's going to update the weights of our agent. So I'm going to say weights update, which will then use the new policy in taking actions into our environment. So this is going to be something that runs every single step. This is something that's going to be running in batches off of the main process here. So that's what we're putting together. We're going to go and code that replay buffer class, which is going to allow our agent to store observations. So with that in mind, let's go ahead and get to it. So we're going to do new file, buffer.py, and in buffer.py we're going to need numpy and torch. So we are going to say import numpy as np and import torch. we're going to call our class. So we're going to say class ReplayBuffer. And we're going to define our init method. And it actually needs a few params here. So we're going to feed in max size. So how big can your buffer be? We're going to feed in input shape. And actions, so number of actions, and device, which we will default to CPU, but is probably going to end up being CUDA a little bit later. All right. We don't need that pass anymore. We're going to go ahead and say self.memSize equals max size. Okay. We're going to say self.memCTR is equal to 0. We're going to say self.stateMemory is equal to np.zeros. So conceptually, what we're going to do here is we're going to go ahead and declare NumPy arrays of our target size. We're not going to try to build, we're not going to build these dynamically as we go. We're just going to reserve, one big block of memory for our buffer, and that's going to be much more efficient than trying to dynamically expand that. So we're going to say np.zeros and self.memSize. We're going to do star input shape, and then we're going to set dtype equals np.uint8. So I want to talk about this for a moment. So np.uint8 is going to force this to be an integer value, which is what we want in this scenario. Later on, we're going to normalize our images. So that's going to take, a value that's over it's basically going to take a max image size. So let's say earlier we saw 117 as a value that comes out a lot. That's I think that's our orange background. So what normalization will be, and you don't have to type this out with me, I just want to show you something. So I'm just going to say img equals 117. Obviously it'll be an array of 117s. So normalizing this, norm will be 117 divided by 255, because that's our max pixel value, and then we're just going to print norm. Okay, again, we're going to get rid of this code in a minute. I just want to show you something. All right, so that's going to turn it into this 4588235, etc. number, and we do that to stop large values from from impacting the network, because a neural network is just a series of matrix multiplications in the background. If you pass in massive numbers, like 254, it may lose the context of what that is, and you just end up with a large number overpowering a small number. So normalization helps avoid that. Now, where's the problem here? Well, we're going to store as int, but we want our network to use these. Well, why don't we just store as float, and we can store this entire float value? The reason we don't store as a float, and I actually started out with this, is if you store this as np.uint8, then your total buffer size with 500,000 images is going to end up being about 16 gigs of memory. And in fact, if you have less than 16 gigs available for this project, If your whole PC is 16 gigs, you may need to lower the buffer size to something a little bit smaller, even with int. If I set this to a float value to hold this big long decimal, then that 16 gigs turns into a little over 130 gigs of RAM. Same data, same level of specificity, but now because we have normalized it and turned it into this float value, we need a machine that can store a 130 gig buffer. And I'm assuming most of you don't have 130 gigs of memory on your machine. I don't. This was actually a problem of some that was causing me some trouble early on, because I was kicking off training and I would come back 30 minutes later and my desktop had frozen up. I could no longer use my computer and I couldn't figure out why. So I finally ran it and then started printing out memory values and saw the buffer at 130 gigs and realized that that's what was going on, that I had used the wrong data type. I had used a float and I was storing a big long float value. So what we're actually going to do, we're going to store everything as int, and then when it comes time to use those values, we are going to normalize them on their way into the network. It's not as clean process-wise. In a perfect world, I would like to be able to store values in a buffer and read them out from the network exactly as they're stored and just have it accept things as they are in the real world. But that is not actually practical with the way we're set up here. So we're going to go ahead and copy that. So this is going to be next state memory. Okay. And then we're going to do action memory. So self.action memory is equal to np.zeros, and this will just be self.memsize okay, and this one can also be dtype np.uint8. And reward memory, actually this one we're going to do float 32 on these. Those won't have the same impact. You can play around with making those uint8 as well. In my original version of the code, they are floats, so I'm not going to deviate from that for now. They probably work fine as uint, but we're going to stick to the one that I know works. All right, we're going to do self.reward memory equals also np.zeros self.memsize and dtype equals np.float32 and self.terminal memory is going to be np.zeros and self.memsize, and dtype here is actually going to be bool. And self.device is equal to device. Okay, that's our init method. We're going to define a can sample method that's basically just, hey, do we have enough to sample? So I'm going to say def can sample self batch size. This is something that you definitely want to play with based on use case. So we're going to say, let me type and then I'll explain it. So if self.memCounter is greater, then we'll say self. Oh, you know what? I also messed something up above, and it's going to equal. Okay. That did not do what I wanted it to. All right. So if this is greater than batch size by 5, then return true. Else return false. Okay, so what we're trying to do here is we're trying to make sure that we're not just training on a very small batch count. So if you only have one, if you have less than a batch in the buffer, you don't even have enough values to return, so we always want that to be false. But then even if your batch size is 64 and you only have 64 values, well, you don't want it to rapidly pull in the same 64 values over and over again and start training on them. You're going to end up with a skewed, a very skewed network very quickly. Right now, I'm playing with this as, batch size times 5 because, we're starting from scratch on the network. If you wanted to be able to, say, kick off training and stop it at some point and pick it back up later, you actually want to increase this number. So you might want it to have 100 times batch size. You might want it to just run for 60,000 iterations without attempting to train, just so you have a good base of information to start with. Starting out with this as a very low number on a trained network is a really good way to turn a trained network into a no longer trained network. So just keep that in mind. This is perfect for starting from scratch. That is a value, though, that you want to tweak if you start working with other, if you needed to pick up training halfway through. All right, so we're going to do store transition, and that's going to take self state action reward next state and done. And here we're going to set our target index. So again, we're not appending, we are keeping track of where our index is, and then we're filling up to that index. When the index gets to the end, it's going to loop back around and start at the beginning. So we're going to say index equals self.mem ctr % self.mem size, and that's the looping part. So basically, whatever your mem counter is, if the mem counter is suddenly, if our total max size, our mem size is 500,000, and our mem counter is 500,001, it's going to loop back around and index will now equal 1. So self.stateMemory, we'll say index will be equal to state, and we're going to just paste that a few times because we're going to be reusing parts of it. Okay, So here, this is going to, actually it's still going to be index. I deleted the wrong part. We're going to say, instead of state memory, this will be next state memory will be equal to, not where I wanted to go. All right, next state memory will be equal to next state. Here, we're going to say action memory and this one's going to be a little bit different. So action memory index is going to be torch.tensor action .detach .cpu. And this is the this is what's actually coming out of our model. That's why that one's a little bit different. All right, and then we're going to do reward memory. And that'll just be reward, not return, reward. And then we're going to do terminal memory will be equal to done. And then finally, we're just going to say self.memctr plus equals 1. Okay, that's our store transition method. Now our final method in buffer is going to be def sample buffer. And this is going to take self and batch size. Okay, and here we're going to go ahead and say maxmem is equal to the minimum of self.memCounter and self.memSize. So basically, we want to know how much actual data is in the buffer. We know that memSize is going to be, the total, that memCounter will start out very small, but will eventually be well off into the millions. And we know that memSize is the total amount of memory that could be in the buffer. So if memCounter is less than memSize, then that's how much memory is available. If memCounter is greater than memSize, then memSize is going to be the amount of data available. So we're going to say batch equals np.random.choice, and we're going to pass in maxmem and let's see. Oh, hang on. All right, we're going to pass in maxmem and batch size. And we're going to say states is equal to self.stateMemory batch. So this is basically going to return a set of indices, and this is going to select those indices. So we're going to say next states is equal to self.nextStateMemory batch. We will say that actions equal to self.actionMemory batch. We'll say rewards. Nope, not resource warning. Rewards is equal to self.reward memory. Batch. And dones is equal to self.terminal memory. Batch. All right, and then we need to convert all of these to PyTorch tensors. So this is going to be states equals torch.tensor states dtype equals torch.float32 .2 self.device. And then really, this is probably where we can do some copy paste just a little bit here. Okay, so this is now going to be next states. Okay, and then this is going to be actions. And actions is going to be equal to actions. And you can keep your data types here. That's going to stay the same. And rewards. Okay. And dones. And this is the only one that we're going to change. So we're going to say dones, and then this is going to be torch.bool. Okay. And then we will return states, actions, rewards, next states, and dones. All right, and at that point, we have our complete replay buffer. I'm going to go ahead and end the video here. In the next video, we're going to go ahead and start working on the agent and the train method. So I'll see you there.